My lecture will be about common language effect size indices that can help us better understand the practical significance of our research findings. So before we talk about these indices, let's take a look at this example. So let's say we have an ability test score, and we have two groups of test takers. And these test takers belong to different racial groups. So race would be coded, one as racial minority and two as racial majority. So let's say we correlated race with the test score and we got a correlation of 0.30. So this correlation will mean that on average, racial majority applicants receive higher scores on the test compared to the minority applicants. Now, if we square this correlation, we get 9%. Right? This is coefficient of determination, which is the proportion of variance explained in the ability test scores, explained by the grouping variable, which is race. So if we look at this 9%, to some people, it may look like 9% is not that big of an effect. So this effect is easy to dismiss as practically unimportant, just because 9% does not look like a whole lot of variance that's explained by race. Now, let's assume that this correlation of 0.30 is based on 50 racial majority applicants and 50 racial minority applicants. So if so, then the covariance D that will go with this R will be 0.62. So what does it mean? Well, it means that the difference between the average test performance for racial majority applicants and racial minority applicants is just a little over half of a standard deviation. Is that a big difference? Again, it does not look like it's a very big difference. So again, this effect, the effect of race on the test performance, does not even look like a big effect. Now, if we convert this correlation or take this covariance D and convert it into a common language effect size index, so we get 0.67, which can be interpreted as follows. If minority applicants and majority applicants apply for the same job, and this ability test score is used for selection purposes, 67% of the time, the racial majority applicant will get the job because of the bias test. Now, this is a more concrete interpretation of the practical significance of this finding. And it also does not look as trivial as 90% of variance explained. So today's lecture will be about common language effect size indices that allow us to interpret our research findings from the practical standpoint. I will use this abbreviation CL to refer to the common language effect size indices throughout the lecture. So common language effect size indices provide an intuitive way of communicating research results to all users of academic research. And that's not practitioners. Not only practitioners, it also includes academics. It includes other users of our research, journalists and reporters who write about research. It can be our students, it can be organizational decision makers, members of general public who are interested in our research results. So CL indices are helpful in terms of communicating and interpreting our findings in practical terms. So we're all well aware about the gap between science and practice. And there have been lots of strategies proposed that we can use to bridge this gap. This is just a quick summary of the strategies. Increase the relevance of research that we're doing by asking and answering questions that actually matter to organizations. Foster collaboration and socialization between researchers and practitioners. Increase the trustworthiness of our research by improving its rigor and ethicality. Disseminating research results through media, classroom instruction, and all other means. But most scholars who have written or spoken about bridging the science practice gap agreed that we need to find ways to interpret and report our research results in a way that is useful and makes sense to all users of academic research, not only to academics, but also to practitioners. So why are the CL indices useful for academics? First of all, we're strongly encouraged to supplement significance testing with the interpretation of the practical importance of our results. And CL indices is just another way of provide another way of looking at our research findings and allow us to gauge the practical significance from a different perspective. That is different from the perspective that's different from the traditionally used effect size indices. Also, CL indices help us address the shortcomings, some of the shortcomings of the traditional effect size indices. There is evidence, that's a paper published at JP back in 2014, showing that CL indices might be easier to understand than some of the traditionally used effect size indices. Also, some traditionally used effect size indices tend to be quite small. That was my very first example in this lecture, showing how proportions of variance might be interpreted as trivial in terms of the size of the effects. So if we only look at the effect size indices that tend to be small in size, it may suggest to some people that our research findings are trivial, organizational theories have low explanatory power, and it will further deepen the science practice gap. For example, Rosenthal and Rubin in their 1982 paper noticed that even experienced behavioral researchers might find it surprising that a correlation of 0.32 that corresponds to 10% of variance explained between the treatment and patient survival is equivalent to a reduction in death rate from 66% in the control condition to 34% in the treatment condition. So some of the traditionally used effect size indices may be interpreted in a way that underestimates the practical value of the findings. Also, if we include CL indices into our toolboxes, it will help us gain a more comprehensive and at times more nuanced understanding of our research results. CL indices are not designed to replace the existing indices. Instead, they have to be used in conjunction with significance testing, with traditional effect size indices, and other ways of assessing the practical importance of our results. So if we use all of these tools together, we'll be able to get a more comprehensive understanding of what our results mean in terms of statistical significance and practical significance. Also, CL indices, as I will show later in this lecture, they can be used to interpret the size of the effects in the regression models with the higher order terms. As of now, we only have R squared and F squared, which is derived from R squared, to evaluate the importance of higher order terms. This is interaction terms and nonlinear terms, which are usually cubic and quadratic in organizational research. So CL indices can be used to look how the magnitude of predictor effects changes across values of a moderator in regressions with interaction terms. And they can also be used to see how the effect of a predictor changes along the curve in regressions with nonlinear terms. So currently, we don't really have an effect size index that can be used to assess the practical importance of simple slopes, the effects that are captured by simple slopes. So far, we have the CL family includes 3 types of indices. CLG that can be used for group comparisons, CLR that can be used to interpret bivariate correlations, and CL beta that can be used with regression models, including regressions with higher order terms. So I'll talk about each of these types of indices one by one. CLG. CLG is used for comparing groups, for mean comparisons. CLG is interpreted as a probability that a score sampled at random from one distribution is greater than a score sampled at random from another distribution. Example from the original McGraw and Wong's paper is comparing heights. In that example, it's an old data from National Center for Health Statistics data set. They compared the heights of men and women. They have a sample of 988 men and 1,066 women. Average height for men in that sample is 69.7 with a standard deviation of 2.8 inches. For women, it's 64.3 inches with a standard deviation of 2.6 inches. Now, if we compute a CLG, and I'll show you how to do it in just a moment, if we compute the CLG for this difference in means, it will be equal to 0.92. So how can we interpret this CLG? We can interpret it as follows. If a man is paired with a woman randomly, the probability that man will be taller than a woman is 92%, or we can interpret it in a even more intuitively, in a more intuitive way by saying that in 92 out of 100 blind dates, the male will be taller than the female. So let's take a look at how to compute the CLG. To compute the CLG, we need to first estimate the mean and the standard distribution of the different scores between the two groups. So if we have men and women, heights for a sample of men and heights for a sample of women, we need to compute different scores between those two groups and then estimate the mean and the standard deviation for that distribution. Mean difference, sorry, the mean of the distribution of different scores can be estimated by subtracting mean of group 2 from the mean of the first group. Standard deviation is estimated as the square root of the summed variances of these two groups. So CLG will be probability of obtaining a score that is greater than 0 in a distribution of different scores. We're comparing it to 0 because 0 will mean no difference between the two groups in terms of their scores. So z-score for difference of 0 is computed as 0 minus m difference over the standard deviation, and then the upper tail probability for this z-score will be CLG, the probability of getting a difference that is greater than 0 between the two groups. Example. I took this example from a recently published JP paper that tested a prediction that multitasking is associated with creativity. So let's take a look at this experiment. There were 3 experimental conditions in this experiment. I will focus on just 2. So we have a multitasking condition and a sequential task condition. In the multitasking condition, participants worked simultaneously on 2 tasks. They worked on a conference call and they were responding to emails. In the sequential task condition, participants completed the same 2 tasks sequentially. Dependent variable was creativity. Assessed is the originality of solutions in the brainstorming task. Participants were asked to come up with all possible uses for an object. And then raters assessed the originality of their solutions. So in the multitasking conditions, the average originality was 3.48 with a standard deviation of 0.87. In the sequential task condition, originality was 3.08 with a standard deviation of 0.86. Now, the difference between these two means was significant at 0.01 level with Cohen's d of 0.46. So if you want to compute CLG, we first need to compute estimate the mean of the distribution of the different scores between these two groups. This can be estimated by subtracting 3.08 from 3.48. Standard deviation of this distribution of different scores is estimated as the square root of the summed variances. And if you do the math here by using the standard deviations, the standard deviation of the distribution of different scores will be 1.22. Now we need to compute the z-score for a difference of 0. 0 minus 0.40 over the standard deviation of 1.22, and we get a z-score of negative 0.33. The upper tail probability, you can get that from a z-score table or using a z-score calculator or an Excel spreadsheet. The upper tail probability here will be 0.63, and this is our CLG. So how do we interpret it? If we randomly pair 100 employees who multitask and 100 employees who perform tasks sequentially, in 36 pairs, a multitasking employee will outperform in terms of their originality and their creativity, will outperform an employee who performs tasks sequentially. If you don't have access to raw data or you don't have means and standard deviations, you can compute CLG from Cohen's t-statistic or correlation between the grouping variable and the dependent variable. And you can convert T and R to D and backwards. So to do this, Dunlop provides table with values of Cohen's d ranging from 0 to 199 and corresponding CLGs. Dunlop also provides a code that can be used to compute the CLGs from Cohen's d. So this is the table from Dunlop's paper. So if we go back to our example here, Cohen's d was 0.46 in this experiment, and the CLG that we computed using this equation was 0.63. So let's use the table to see if our results will match. So Cohen's d was 0.46. So the estimated CLG is 0.63, which is exactly what we found by doing the math manually.